type, you have your what? The first capacitor this way, then the second one, then you know, of course, you have your Q1, C1, Q2, C2. Now, if you have to actually obtain the total what? Capacitance, if you have to actually obtain the total what? Capacitance in this calculation, what do? You say your QV total equals to V1 plus V2, meaning that the total voltage here plus the total voltage here, when they are being added, you obtain your V total here. Now, if you are to use this, what do you now say? Recall that your Q equals CV. So if Q equals CV, then V will become Q over C. It is this Q over C that you substitute into all this your V total. From there, you now have your Q over C total. You know, it's the potential. I mean, the capacitance you're actually looking for. So it's the one that will carry the total. Then when you substitute this in, you have Q over C total. Then you have Q over C1 plus what? Q over C2. Of course, these are constants. So when you cancel them out, you'll be able to now have something like this: 1 over C total because 1 over C1 plus 1 over C2. This is the actual formula for what? Total capacitance in a what? Series connection in a what? Electric circuit. You understand? So for series connection, you have the resultant formula. And let me bring this in. If peradventure you have three capacitors being arranged, you understand, in series connection, what do? You just make sure the formula. Let's say you have something like this, probably the third one, Q3, C3. What do you have? You just add it here to get 1 over C3. That will be your total. So it's as simple as ABC. Just know in your mind that if you see a circuit that has resistors, you understand, for resistors, the formula is straightforward. Resistors in series connection, you have to use the opposite of this. Resistors in parallel connection, you have to use the opposite of this formula, which is the CT equals C1 plus C2. So that is all about your series and parallel connection of your what? Capacitors. So I want to believe justice has been done to that, so that each time you come across questions, and of course we are going to treat 1 or 2 questions based on capacitors arrangement. You understand? So before we move to another topic, let's go to another one. When you talk about the energy stored in your what? Capacitor. You get? How do you obtain the energy stored in your capacitor? Now at this junction, you know that your work done. Work done. What is work done? Work done is force times perpendicular distance. Right? Now if your work done is force at perpendicular distance, how do you now relate your work done with what? Electric field. Do you understand? Work done with your electric field. So automatically, instead of you using your force, you use your what? Your charge. So instead of using your force, you make use of your what? Your potential difference. Now instead of using your what? Distance, you make use of your what? Charge. Or you write it this way: V multiplied by what? Charge. So if you are to turn it around, you have it as what? QV. This is the total work done in your what? Electric circuit. But in this case, we'll be looking at the average. Now, if you look at the definition says the work done in storing a charge in your capacitor is defined as the average potential difference. So it's the average potential difference we are looking at. So in this case, now it says, so therefore your V is V average. Hope I get it. So when you substitute this into V, you're going to have your work done to be what? RQV. So this is the actual work done. You say actual. This one is the one we have here is what we call total work done. You might want to ask me, what's the difference between total work done and actual work done? Good question. For your total work done, we are not actually looking at some specific region. You understand? We are not looking at a specific region in your capacitor. We are looking at the total work done in the whole of your capacitor. But in this case now, your average work done, the actual work done is work done that is being explained at an infinitesimal. When I say infinitesimal, don't worry, as you advance in science, you'll be hearing different scientific words, infinitesimal or instantaneous. When I say instantaneous, it's just at that specific spot in the what? In the confinement of a capacitor. If you are looking at the work done that is being experienced at that specific point in the confinement of a capacitor, then you won't be looking at your total work done, because you are not looking at the whole of the capacitors or what at a particular region. Then you never will, I mean, you are never expected to use your total work done, but what the actual work done. That's just the breakdown. Now let's look at some example. That example says calculate the energy stored in and the charge. Calculate the energy stored in the circuit and the charge in the plate of a combined capacitor in the circuit. Look at it, very simple. If you have a circuit like this, look at it. If I will ask you what type of arrangement is this? This is definitely a parallel arrangement of what? Two charges, 5 microfarad and 5 microfarad. You can see now the volt potential difference being put at the bottom here is 100 volts. Now what are we asked to calculate? You have to calculate the energy stored. That's one. Number 2, you are also supposed to calculate the charge in the plate. Of course, I want to believe that your 5 microfarad, that's your what? Capacitance. Abi? So we say your Q is CV. So you get, so you are told to calculate the charge in the plate. So what we are given is capacitance. We are also given what? Potential difference. So we are expected to calculate the charge in the plate. So let's start with number 2, question 2. Now of course, in physics, we are expected to always write down all your parameters. So you say my C1 is what? 5 microfarad, and my C2 is also 5 microfarad. While my potential difference is what? 100 volts. Now how do we go? For my C1, 5 microfarad. Remember I told you what's micro? Micro is 10 raised to power minus 6 farad. Then the second one, 5 times 10 raised to power minus 6 farad. We have settled that. Then we already have our potential difference as what? 100 volts. So how do you calculate the total what? Capacitance. So you say, recall. What are we recalling? That the what? The circuit. Let me use the number D. The circuit is what? The circuit has parallel what? Parallel connection of what? Capacitors. So if it has parallel connection of capacitors, what will be the total capacitor or capacitance? So the C total will give you a C1 plus what? C2 straight up. So what do? 5 micron plus 5 micron will give you 10 microfarad, which is equivalent to 10 times 10 raised to power minus 6 farad. So we have gotten total capacitance. The total capacitance and potential difference we already have. So if we want to now obtain the charge, what do? You say your Q, which becomes CV, right? Now if Q is CV, then all you just need to do is multiply your what? 10 exponential minus 6, and that's your C total. Then times the potential difference, which is what? 100. What do? For your indices, from there you have 10 raised to power 3 times 10 raised to power minus 6. From there you have 1000. So that will be your charge. From there you have 1000 coulomb. Now if you are to solve question 2, what does question 2 say? Question 2 says you should obtain, if you want to solve question 1, we solve question 2. Energy. So the average energy is given as what? Half Q V. Right? Now that's the half Q V. So you just put half dot Q V is what? What's Q V? 1000, which you've obtained. Then your potential difference, which is what? 100. If you divide this, that's 50. So 50 times this will give you 50,000 joules. So that will be the energy obtained. So it's as simple as that. You can see easily it's all being broken down. So you can also attempt some other questions on capacitance, capacitors, and you discover that easily the questions will be solved. Now let's proceed to what are the applications? What are the applications of our capacitor? Number 1, tuning of what? Radio circuits. You understand? You check a radio circuit if you like. When I say radio circuit, if you open the knob, the cover of your radio, the panel, there's a place we call like a motherboard. If you have seen a computer before, the inside of a computer, now there's some arrangement on this board. There are so many we call it what? Chips. Call it microchips. Now on this board, if you check very well, you definitely see your capacitor hang somewhere. You understand? You know, of course, on this we have a lot of wire connecting a lot of other things. We have the wire that goes to probably the speaker ahead. We have wires that goes to your speaker. We have wires that goes to your control knob. We have wires that goes to your stereo. All being arranged on this motherboard. Now, if you check properly, you definitely see your capacitor. Now, what does your capacitor do? It helps to store charges for your device. Now, the second point is that smoothing rectifying current from DC power supply. If you check your normal general electricity supply, which we all know as PACN, PACN supplies what we call DC current. They supply direct current. So if you check your meter or somewhere in your electric connections, probably at home, you definitely see where your capacitor is actually what being used properly. Now the third point is elimination of what? Sparkings. You understand? Or sparks. Elimination of sparks in what? Switches. So at this junction, there are some questions there for you to actually lay your hands. We have 3 good questions. Let me break it down for you to understand. The first one says calculate the magnitude of what? Electric field intensity between 2 plates 15 cm apart if the potential difference between the plates is what? 4.2 volts. You can see that's very much simple. Now number 2, what's the effect? What is the effective capacitance in the diagram above? You understand? Now what diagram are you seeing? I'm going to solve that because it looks a little bit technical. Please.